Good morning and welcome back. This is Electrodynamics second semester. Today, this is Electrodynamics 21.520. Today, we will cover the second part of section 3, covariance of electrodynamics, from page 47 to 52. Not too much. Before we start, I would like to briefly review what we have learned so far. Go back to page 1, just a brief review. We say Newton's law has been radically modified, but electromagnetic laws do not need any modification, but we need to change the form and to demonstrate they satisfy Lorentz transformation. Okay, for example, we define full current and conservation of charge here. That's conservation of charge. And we also define full potential. That's the full potential. And Lorentz gauge wave equation, inhomogeneous wave equation. We define a full wave number, and we say that it's invariance of the phase. And we define field tensor, field strength tensor of the second rank. E field and B field now can be expressed as a full tensor of the second rank. F alpha beta or F alpha beta differ slightly. And the Maxwell equation now can be expressed as this form: divergence E, Gauss law, curl of B, Ampere's law with Maxwell correction. And what else? Divergence B equals 0, Faraday's law. And here is the SI unit. Okay, so E field and B field are transformed through these relations. And we talk about the force equation, the equation of motion, dP dt equals E times E plus 1 plus here. We learned these relations. That's the Lorentz force. So Lorentz force can be derived from these 4 vector equations. 4 tensor of the same rank. Therefore, this equation will be correct. And that is the rate of change of the energy. Okay, satisfied. Everything looks good. So we will continue our discussion about conservation of, actually is a Poynting vector and conservation of momentum. In a similar manner, we can demonstrate the covariance of the conservation law for field and mechanical energy and the field and mechanical momentum. Mechanical energy, field energy, mechanical momentum, field momentum. Remember, we have a 4 momentum. Maybe we can use the idea of 4 momentum to this case. And to demonstrate the covariance of the conservation of energy and momentum. To demonstrate the conservation of energy, we need to introduce the Poynting vector. To demonstrate the conservation of momentum, we need other knowledge. Okay, so actually this part is a homework, so it's not very bright. It proves. I'm sorry, in this PowerPoint I use a iPad together with notebook. My iPad cannot display PowerPoint file correctly, especially the equation. So I use PDF file. If you know how to display the equation correctly, please let me know. I hope next time I can use PowerPoint file, because with the PowerPoint file, I can display correctly. If a physical law can be expressed as a relation between four tensors of the same rank, then its form is invariant in form in all the Lorentz frame. Okay, so first let's define symmetric stress tensor, not field tensor, but stress tensor. So theta, alpha, beta is related here. Sum over lambda, sum over lambda, sum over mu, sum over lambda, sum over mu. Okay, looks similar. That's equation 12.113. And partial alpha, theta, alpha, beta is here. It's not a proof. It's not a rigorous proof. Just show you how to prove. If you want to do that, is that you will win. You will get extra points, 5 points at most. Beta equals 0. We have these relations. You can imagine this one and this one is the same. That's related to field intensity, U. Field intensity. And these two are different. There will be pointing vector. And this is field, this is current. So there will becomes J dot E. Okay. They have a simple relations. That's conservation of energy. Just a simple proof satisfy the conservation of energy. How about the conservation of momentum? It's not that easy, not very clear. So it's an extra point, extra bonus. Please derive conservation of momentum by yourself. Okay, that's the first part. That's in a similar manner, we can demonstrate the covariance of the conservation laws for field and mechanical energy. And this is very important. Maybe you may have a chance to see, to demonstrate, to prove that you understand what happened here. You understand how to prove conservation of momentum at the final exam. Okay, more information. Now, let's consider the general form of the relativistic equation of motion. dP over dt equals force, where force is any force, such as gravitational force. I will give you two examples. First, remember we have two definitions. One is dP over dt. That's the ordinary force. The other is dP over d tau. That's Minkowski force. Okay, consider the general form of relativistic equation, this one, where force is any force, such as gravitational force, Lorentz force. If the force and velocity are parallel, what will happen? We should differentiate with respect to gamma as well as v, because gamma is also a function of v. Okay, by doing so, here, there will be the acceleration. The gamma over dt is shown here. The gamma can be write into this form, minus 1 over 2 here, because of this one minus 1. And this one gives us 2v c squared dv dt. So what we have here is gamma cubed minus, so it's v over c squared, v over c squared. So gamma squared, v squared plus gamma. So it's gamma squared times v, so v squared. Gamma squared, v squared over c squared plus 1. This will give us this one. So eventually we have gamma squared. Gamma squared times gamma here. So we have gamma cubed. So for the parallel motion, constant force does not cause constant acceleration. If particle move in this direction, and you want to accelerate in this direction, you need a lot of force. Not that easy. Okay. However, for the perpendicular force, it's relatively easy. It's constant as in uniform circular motion, F here. In this case, gamma can be considered as a constant, just like singleton radiation. So for the singleton radiation, we will classify into these two cases. For the acceleration, we will use this one. For the radiation, we will use this one. Okay, that's for the singleton radiation, 同步辐射. We will discuss these issues at chapter 14. For the singleton radiation, we have accelerator, follow this rule. We have radiation by changing its direction. We use this idea. Okay, to approach, change the radius, change the curvature, we use special case 2. Accelerate, we use special case 1. Okay. Now, I want to give you 2 examples. The problem 1 is a police radar operates on a frequency of omega. Police radar. What is the frequency received by the police? What is the frequency received by the police after the signal is reflected from a car moving at velocity v0? That is, the police is chasing a car and the car moves at a velocity v0. So the police send a signal, frequency omega with number k. The signal will be bounced back, reflected from the car moving at a velocity. So we can divide it into 2 steps. Step 1, in the police frame, the radar sends a signal omega k toward the car, which is moving at velocity v0, direction shown in the figure. We can transform omega to the car frame. So the car will see the signal. Car have a relative motion here. So he will see a signal. They have a relative motion. If kz omega prime, we police frame, car frame, where kz is the component of k along B0. So along B0, therefore kz will be k cosine theta here in the z direction. So last omega prime will be here. Gamma 0 omega kz v0. Kz, k, we know k. Kz is shown here, omega over c, and v0 is here. So we can group gamma 0 omega. So it's 1 minus v0 cosine theta over c. This is the Doppler shift frequency detected by the car. If car has a radar, police has a radar, and a car has a radar, then he will receive a signal, a frequency like this one. This is also the frequency of the wave reflected by the car, as seen in the car frame. Okay. Step 2. In the car frame, see the figure. Car sends the reflected wave with omega prime and k prime back to the car at the frequency. So omega prime equals gamma 0 omega here. So in the car frame, the police is moving at velocity v0 toward away from the car, relative to the car. The transformation omega prime to the police frame, we obtain the frequency observed by the police. It's Doppler shift again. So omega double prime will be here. Just substitute omega 0 and k prime to this equation. K prime here is omega prime related to k prime is omega prime over c. Okay, but with a cosine theta. Kz, okay, it differs slightly. And so we can write, we have 2 squared here, gamma 0 by substituting omega prime to here. We have gamma 0 squared omega 1 minus v0 cosine theta over c squared. So the police velocity, the car's velocity is relatively small. Therefore, we can simplify the calculation using these relations. So eventually we got this relation easily. In the radar frequency, 1 gigahertz, and the car moved away from the police. Normally, they are in the same directions. So for our convenience, they are in the same direction. So theta is 0. And police car, the car drive very fast, 150 kilometers per hour. So we should calculate omega change to frequency 1 gigahertz. Okay, so let's see the frequency change. V0 here. V0 is 150 kilometers per hour equals to roughly about 40 meters per second, roughly. And 40 meters per second, cosine theta is 1, 2 V0 over C, 80 meters per second. And the speed of light is 3 times 10 to the 8th meter per second. And remember what we have 1 gigahertz. Okay, so this one cancel with 1 gigahertz, 80 meters per second. 1. Okay, cancel. So it's 7. Cancel. So just 2. So it's roughly about 800 times 3. So roughly about 278 hertz, the frequency shift. Inconvenient. The same, okay. So we can also, the police can detect the speed of the car from the frequency shift. From the shift of the frequency, we can derive, we can calculate, we can detect the car speed here. Okay, that's a radar detector. Problem 2. Problem 2. Let me read the problem 2 for you. An observer in a laboratory sees an infinite electron beam of radius A and uniform charge density rho. So at a rest frame, he sees the uniform charge density rho, and the charge is rho, moving actually at velocity v0. So we know the relation of the rest frame v0. So say z equals v0 rho, okay? So at the rest frame, if you move with the electron beam, you will see no current because you just see the charge distribution only, but no current. Therefore, assume what force does he see on an electron at a distance r from the axis? R is inside. You can consider R as inside or outside. A distance r from the axis. So in this case, you will experience actually rho will generate E and J will generate B. So you will experience both electric field and magnetic field. But if you move with the electron beam, you just experience electric field only. So let's calculate electric field first, and then transform, use Lorentz transformation, transform to E field and B field. Okay, the problem can be readily solved in the left frame. here we will take a long route for an exercise. Just in the left frame, you have rho, so you can calculate D, E, and you have J, and J equals here, so you can calculate B. But here we take a long route, 绕道比较长的路 for an exercise on some of the transformation equation just derived. 就是为了利用狭义相对论的那些知识，我们绕一下远路，先绕到比较简单的particle frame 或者是 beam frame. So the current density J in the left frame is shown here. Rho has a negative value because an electron beam. Okay. By 37, we have the beam frame here. At the beam frame, no current prime system move with the electron beam. Rho prime will become here. What happened? If you move with the particle, you will see the density is actually smaller, because when you move a moving particle, it will become shorter, so it's length contraction. However, inside, you will, if you move with the particle, you will see a so-called proper length. Therefore, your charge density will be decreased. That's why we see that the left frame rho is greater than the beam frame rho prime by the factor gamma 0. This is because every unit length of the beam is in its rest frame is length contraction. Okay, to its rest frame. Okay, in the beam frame, you will see here. Hence, there is only radial electric field, only electric field. So from here, you can calculate the E field. So E field here, inside the beam is 2 pi rho gamma divided by gamma 0. We know it's perpendicular electric field. We transform perpendicular electric field only because parallel electric field 0, parallel B field 0 because no current, perpendicular B field 0. So here, all we need to control is this one, parallel components, perpendicular components. So we now transform E perpendicular into the left frame, E prime and B prime, by using the reverse transformation equation. That means we change back. So use reverse transformation that differ in plus and minus V only. So if it's not clear to you, go back to here. Go back to here. From here to here. And now we from here to here. So it just differ by a minus sign. So it's become negative, become positive. Negative and a positive. Okay, so that's why we have a different sign here. Gamma 0 E perpendicular prime. So here, the electric field is still the same. And magnetic field will be rho V is the current. Rho V is the current in the Z direction. The force F on an electron in the left frame is here. That is the force, okay? Lorentz force. the traditional, the ordinary force, Lorentz force. E is the E is positive here because we use minus E to express an electrons. For an electron beam, rho is negative. So we have E because repulsive force. And we have B, that's the Lorentz force, V cross B. And what is the relation here? Okay, so eventually these two have a simple relations because Z times theta is in R directions. So they have a simple relation here. They have a repulsive force in the R directions. Okay, that's the end of chapter 11. Our TA will provide the solutions for you, and we will also upload a file to YouTube so you can study by yourself. Thank you very much for your help. Thank you very much for your cooperations.